Okay, let's start my presentation. My name is Tomotaka Kuwahara. First of all, I would like to give thanks to Steve Vision Glory Church for providing me this great place and the equipment. My affiliation is Riken AIP, and the presentation title is Lieb-Robinson bound and almost linear light cone in long interacting boson systems. This work is a collaboration with Keiji Saito in Keio University, and this work has been uploaded on arXiv in 2021. First of all, I will show the research motivations. The motivation is Lieb-Robinson bound, which characterize the speed limit of the information propagation. Here, let's consider a time evolution of one on-site operator, which I denote by OI. Then, after the time evolution exponential of IHT, the operator OIT is no longer a local operator. Our purpose is to approximate this operator OIT onto a local region, which is denoted by the ball region centered at the site I. We denote this ball region with radius r as I bracket r. Then we aim to estimate the approximation error between the OIT and the approximated one OIT I bracket r. The Lieb-Robinson bound gives a general upper bound on the approximation error. The Lieb-Robinson bound is quite general and can be derived independent of the system details. For the Hamiltonian with two-body interactions, only the two conditions are assumed. Here the Hamiltonian is given by this form, and Hij is a bipartite interaction, and Hi is the on-site potential, and the result is generalized to arbitrary k-local Hamiltonians. The first condition is the short rangeness of the interactions. This condition is relaxed to the exponentially decaying interactions. The second condition is that the one site energy is finite. This mathematically means that the Hamiltonian is locally bounded. These two conditions are typically satisfied in quantum spin systems with small spin number, for example. And under these two conditions, the commutator norm is bounded like this inequality. The commutator between the OIT and the other OJ. Then the commutator decays exponentially with the distance between the site I and site J. By using this Lieb-Robinson bound, we can also ensure that the approximation error decays exponentially with the radius r. In the previous slide, I have shown that the Lieb-Robinson bound can be derived by using these two conditions, this one and this one. But the condition often breaks down in realistic experiment, and we have a natural question on what happens when one of the conditions breaks down. In particular, we are interested in the form of the effective light cone. The effective light cone is a characteristic length to achieve a good approximation error for OIT. In the standard Lieb-Robinson bound, the form of the effective light cone is linear with the time. So the effective light cone is given by this equation. This V is the effective sound of the information propagation. We refer to such a linear light cone as the linear light cone. When the first condition breaks down, the interaction becomes long range. I mean the power law decay of the interaction. In this case, the form of the effective light cone strongly depends on the decay rate of the power law interactions. On this case, by recent progresses in these 2 years, various kinds of universal properties have been revealed. On the other hand, a typical example for which the second condition breaks down is interacting boson systems. Until now, the Lieb-Robinson bound in boson systems has been an extremely challenging problem. In this talk, the breakdown of the second condition, I mean the one-side energy is finite, is our main research target. Okay, now I will show the setup of our systems. We consider the generalized Bose-Hubbard model in this form. Now, lattice systems with a finite dimension, capital D, is considered. The first term, this term describes free boson terms, and the second term describes the boson-boson interactions. This operator Ni hat is the boson number operator on the site I, and the function f is an arbitrary function for the boson number operators. But we now assume the interaction is finite range, so the number of boson number operator which is included in one function f is finite. Now Ni1, Ni2 to Nik is adjacent boson number operators. Okay, then by choosing this function f appropriately, this Hamiltonian reduces to standard Bose-Hubbard models. For the Bose-Hubbard model, we can define the one-side Hamiltonian like this form. Then, if n bosons concentrate on one site I, for example, then the local energy is roughly proportional to the square of the boson number n, which is because of this square independence of the boson number operators. Thus, in the thermodynamic limit, the total number of bosons is infinitely large, and hence the local energy can be also infinitely large. I mean, the n can be infinitely large. Of course, it is quite unlikely that all the bosons concentrate on one site, but it is quite a challenging task to exclude the possibility in mathematically rigorous ways. Okay, now in this slide, I will summarize several previous works on the Lieb-Robinson bound in boson systems. The simplest way to derive the Lieb-Robinson bound in interacting boson system is to restrict the boson number on one site. For example, in the hardcore boson models, only one boson can sit on one site. So in this case, the assumption of the finite one-site energy is recovered, and we can easily obtain the Lieb-Robinson bound by using the standard Lieb-Robinson bound technique. Practically, it is very natural to believe that many bosons concentrate on one site is unlikely, but it is not easy to provide a theoretical guarantee to these restrictions. The second example is the non-interacting bosons. In this case, the one-site energy is still unbounded, but we can treat each of the bosons independently, so the Lieb-Robinson bound with linear light cone has been obtained. The representative example of the non-interacting boson is a quantum harmonic oscillator. Other non-trivial example is the spin boson models, where a spin system connects to a non-interacting boson field. Then the boson field interact with each other by the coupled spins. But in this case, one can also prove the Lieb-Robinson bound with linear light cones. Then, how about more general cases? Unfortunately, one can come up with a counterexample such that the speed of the information propagation is arbitrarily fast. In the very famous example by Isart and Gross, it has been proved that there exists 1D boson models with translation invariance which allows the exponential speed of the information propagation in arbitrarily low energy states. That is, distance where the information is propagated increases exponentially with the time. However, the model in the Isart Gross counterexample is quite unnatural, and we still have a hope to prove the finite speed of the information propagation in realistic quantum many-body interacting boson systems. The most important class of the interacting boson system is the Bose-Hubbard model. Actually, the first experiment in 2012 to observe the effective light cone in the Lieb-Robinson bound was achieved in the Bose-Hubbard model. Even though the Lieb-Robinson bound in the Bose-Hubbard model has not been established so far. In this model, as long as I know, the most general and the stronger result has been given by Schuff, Harrison, Osborne, and Isart in 2011. There, they consider the diffusion of the initially concentrated bosons in the vacuum. Now the concentration is region given in the region X. In this setup, we can prove that the boson number operator, away from the initial region X, decays exponentially with the distance djx, which is characterized by this inequality. So we can prove the Lieb-Robinson-like bound for these situations. The upper bound implies that the boson number operator may generally obey the Lieb-Robinson bound with linear light cone, even in more general setups. Unfortunately, the condition that the boson initially concentrate on the vacuum is crucial condition, and no generalization has been known. For example, it is even hard to generalize the result to the case of the Mott state, where the finite number of bosons sit on one side. Our purpose in the study is to prove the Lieb-Robinson bound in more realistic conditions. In this study, we consider propagation over perturbation to a steady state. A state law is initially time independent, so satisfy this equation. Also, we assume that the state law satisfies the low boson density condition. Roughly speaking, this means that the probability distribution of the boson number on one side decays exponentially with the number of bosons. Mathematically, this condition is given by this inequality. Then we apply a local perturbation to the state law and analyze how fast the perturbation propagates to long distances. For example, we apply a local measurement on the site I. Now OI is a projection measurement. Then, after the time evolution, the effect of the measurement propagates to the distance regions. As an important remark, this setup includes quench dynamics to a steady state. For example, the system L and the system R are decoupled at the initial time, and they are given by the semi-equilibrium state. Then, at the time t is equal to 0, the interaction between the system L and the system R is switched. Then, the interaction creates a correlation between the system L and the system R. The Lieb-Robinson bound plays a central role in how long the correlation between the system L and system R propagates after time t. The main result in our study is given by this inequality. For an arbitrary operator OI, the time-evolved operator OIT is well approximated by another operator supported on the the region IR. This IR is the ball region at the center of the site I with the radius capital R. From this inequality, we can easily see that as long as R is larger than t times square of the logarithmic of t, the approximation error is sufficiently small. This implies that the almost linear light cone up to the logarithmic correction has been obtained. As a simple application of this inequality, we can prove the clustering theorem. The rapid decay of the bipartite correlations for the gapped ground state. Here, the ground state satisfies the low boson density condition, and because the Lieb-Robinson bound in this case is slightly weaker than the standard Lieb-Robinson bound, the decay of the correlation is given by the sub-exponential form instead of the exponential form, which is proved for standard spin quantum spin systems. Also, we estimate the computational cost to simulate the quench dynamics on one-dimensional systems. We can estimate the computational cost increases exponential of t times log t to the power of 3. In standard quantum spin systems, this cost is slightly better than this estimation, at most of the exponential of t times log t. Finally, I will show the proof idea. The first idea is the decomposition of the total time to small pieces, the delta t, and connects the approximation step by step. Now, each of the time step delta t is at most of order 1. We start from the operator OI0 on-site operator, and in the first step, we consider the time evolution of the delta t and approximate OI0 delta t by using another operator on the subset x1. x1 is a ball region with a radius delta r. Then, in the next step, we also consider the time evolution of the OX1 delta t and approximate it by using another operator on the subset x2, which is the ball region with the radius 2 delta r. By repeating this process, we can prove this inequality. Each of the time steps is at most of order 1, so the problem now reduces to the estimation of the short time Lieb-Robinson bound. The condition of the time independence of the state law is utilized in this step. In the second idea, we estimate the small time evolution. We here consider general operator OX on an arbitrary subset X. The first point is that in short time evolution, we can ensure that the low boson density condition for arbitrary site we can ensure the low boson density condition for arbitrary site if they are sufficiently separated from the region X. In order to prove this statement, we use a similar method to the one by Schuff, Harrison, Osborne and Isart in 2011. Then we construct an effective Hamiltonian by truncating the boson number in a particular region L tilde. This L tilde is sufficiently separated from the original region X. Because of the low density, low boson density condition, we can ensure that the time evolution by the original Hamiltonian is close to the time evolution by the effective Hamiltonian. In the effective Hamiltonian, the one-site energy is finitely bounded in the region L tilde, and we can apply the standard technique of the Lieb-Robinson bound to this Hamiltonian. The important point is that the Hamiltonian is locally bounded only in this region L tilde, but it is enough to prove the short-time Lieb-Robinson bound only from this upper bound for the local energies. By using these ideas, we can prove the local approximation inequality for the OXT for sufficiently small t. So by using this inequality to the decomposed error in the small time evolution, we can prove our main theorem. Okay, so I will summarize the talk. We consider the interacting boson system, which is given by the generalized Bose-Hubbard model by this Hamiltonian. For this Hamiltonian, the one-site energy is unbounded, and the system does not satisfy the standard assumption for the Lieb-Robinson bound. If we consider a steady state with low boson density condition, the speed of the perturbation propagation is characterized by almost linear light cone as t times square of the logarithmic of t. The Lieb-Robinson bound is described by this form. Open question is to identify the optimal condition in which the linear light cone is ensured in arbitrary Bose-Hubbard type Hamiltonians. In particular, it is quite intriguing questions whether the condition of the time independence of the initial state and the low boson density conditions are essential for the finite speed of the information propagation. That's all of my presentation. Thank you for listening.